talking about solving quadratics by factoring, completing the square, and the quadratic formula. So let's do a little bit of the review on factoring. If I had a problem like this and it asked me to solve by factoring, first thing I'm going to do is I'm going to factor out a -1. So that leaves me with x squared minus 11x plus, this is going to be a plus here, sorry about that, plus 30. And then if I factor this down, I believe it factors down to x plus 5x plus 6. I still have the -1 in front, but it's not going to change my answer. So my answers are going to be x equals -5 or x equals -6. Now, if I have a number in front of the x squared other than 1, then I'm going to use what is called the cheater method to factor. So I'm going to factor it out. I'm going to start off with whatever's in front here. So I'm going to go 2x, 2x, but that means I'm cheating with the 2x. So at the end, I'm going to divide a 2 out at the very end. So then I multiply the outer terms together. So 2 times 12 is 24. What two numbers multiply to 24 but add up to -25? Well, -24 times -1 is 24. -24 plus -1 is -25. So -24, -1. And then I'm going to have to divide a 2 out of one of the parentheses. So this is a parenthesis I choose. So that gives me x minus 12 times 2x minus 1. So my solutions would be x equals 12 or x equals 1/2. So solving quadratic by factoring. Then we also solve a quadratic by completing the square. So if I take a look at this problem, the first thing we did is I would rewrite this as x squared minus 6x plus something. I'm going to put a dash there, is equal to, and then I would move the -2 over, so that gives me +2. And then whatever I add to this side, I have to add to this side. Well, what am I going to add? Well, half of 6 is 3. 3 squared is 9, so I'm going to add 9 here. I'm going to add 9 here to keep the equations the same. I'm going to factor this. This becomes x minus 3 quantity squared is equal to 11. I'm going to take the square root of both sides. So I'm left with x minus 3 is equal to positive square root of 11 or negative square root of 11. I'm going to add 3 to both sides to get x by itself. So my answer is going to be x equals positive 11 plus 3 or negative square root of 11 plus 3. Then we also talked about solving by using the quadratic formula. Let me do this one over here. A would be 1, B would be 2, I'm sorry, A is 1, B is 10, C is equal to 9. Quadratic formula is -b plus or minus the square root of b squared minus 4ac all over A. So if I plug my values in here, I end up with -10 plus or minus the square root of, well, 10 squared is 100, minus 4 times 1 times 9, or 36, over 2 times A, which is 2. 100 minus 36, isn't that 64? So I end up with -10 plus or minus the square root of 64 over 2. Square root of 64 is 8, so I've got -10 plus 8 over 2, or -10 minus 8 over 2. Well, -10 plus 8 is -2 over 2, which would be -1. Or -10 minus 8 is -18 divided by 2, which is -9. So those would be my two solutions using the quadratic formula. This week, we're going to be talking about complex numbers. And I'm sure most of you have seen imaginary numbers before, hopefully in Algebra 2, probably in pre-calc also. We're going to use the imaginary unit I to write complex numbers. We're going to add, subtract, and multiply complex numbers. We're going to use complex conjugates to write the quotient of two complex numbers in standard form and find complex solutions of quadratic equations. The imaginary unit I. Imaginary starts with I. That's why they use the unit I believe. This is the biggest thing that you have to understand. I is equal to the square root of -1. I squared is equal to -1. Those are the two biggest things you have to know when you're dealing with this, because if you don't know these two facts, you're not going to be able to use imaginary numbers to solve problems or to simplify. And if you're dealing with imaginary numbers, you want to write everything in standard form. Standard form is a plus bi. So if they gave me something like -5 plus negative square root of 9, well, we were always taught that there's no such thing as negative square root of 9. But nowadays that we deal with imaginary numbers, anytime if you have a square root with a negative, you just want to rewrite it with an I on the outside and then take the negative out of there. So it's really the square root of 9i. And then the square root of 9 is 3, so this really becomes 3i. So the square root of -9 is really 3i when you simplify it down. So if I wanted to rewrite this, this would be -5 plus 3i. This is in standard form, standard complex form, because you have your whole number out front and your imaginary number behind. Definition of a complex number: let a and b be real numbers. The number a plus bi is called a complex number, and it is said to be written in standard form when it is a plus bi. The real number a is called the real part, and the real number b is called the imaginary part of the complex number. So if we're talking about all of the sets of numbers that you guys probably have learned in your life, probably learned real numbers, imaginary numbers. Now we have complex numbers. Imaginary unit, again, if it's a complex number, it's a plus bi. We can do mathematical equation, or we can use mathematical like addition, subtraction, multiplication, and division with complex numbers. And when you do so, and we'll talk about that in a little bit here, operations with complex numbers, we can add complex numbers, and when you add complex numbers, you just add the real part and you add the imaginary part. When you subtract the real part, you subtract the imaginary part. It's not real difficult. It's basic. I mean, because you can think of I as just a variable. I mean, you can't add, you can't, if I gave you something like 2 plus 3x plus 4 plus 2x, you couldn't add this 3x to the 2, but you can definitely add these together, and you can definitely add these together. Same thing with a complex number. If I gave you something like 2 plus 3i plus 4 plus 2i, we can add the 2 and the 4 together. That gives me 6 plus 3 plus 2i is 5i. You can add the two parts together. You can add the real part and you can add the imaginary part together. And that's just basically what they're saying here, is that we can add the real and the imaginary parts together. So here's some examples. If I had 4 plus 7i plus 1 minus 6i, well, this would just be 5 plus 1i. So 4 plus 1 is 5. 7i plus negative 6i, that's 1i. If I have 1 plus 2i plus 3 minus 2i, well, that's just going to be 4. Just 4, right? Because the 2i and the minus 2i are just going to cross off. So it just goes away. If I have subtraction, I mean, it's the same as if we were doing a regular subtraction problem, but I would still put a 1 in front of here, and I'd put this as here, and I'd do the same thing here, and I'd use distributive property. So this would be 3i plus -1 times -2, that's 2, plus -3i, plus, and then I'd multiply this through, that gives me -2 plus -5i. And now I would combine like terms, so 3i, -5i, well, that gives me -5i. And then I have the 2 and the -2, well, that's 0. So really, I'm just left with 0 plus -5i, or 0 minus 5i, or you could just write it as -5i. All of these are exactly the same way. This is written in complex form because you have the a plus bi, but it doesn't have to be. It could just be written like this. This problem here, again, I'm just going to put the -1 out in front. So this is going to be plus -7 plus -1i. And then here I have 3 plus 2i plus 4 minus I. I'm going to change that and make that. I'm going to put a 1 in front of there also. So now I'm going to add the whole number, or the real number. So 3, 4, 7, -7, that's 0. I've got 2i, -1i, -1i. That's 0 too, also, isn't it? So I guess that this whole thing right here just simplifies down to 0. That's it. One of the practice problems from this week, we have 14 plus 20i plus 19 plus 2i. Write the result in complex form. So 14 plus 19, what is that? 33. 20i minus 2i, that's 18i. So 33 plus 18i, 33 plus 18i, it looks like letter A. Now we can also multiply complex numbers just like we normally would. So here I could multiply through here. So 4 times -2, that gives me -8. 4 times 3i gives me 12i. That's not too bad. Now this is FOIL, so I have to use FOIL here. So I'm going to multiply 2 times 4, which is 8, plus 2 times 3i, which is 6i. Then I can multiply. I'm going to put a negative here. Okay, it's a -1i. So that gives me -4, plus -4i, and then -i times 3i squared. That gives me -3i squared. But what is I squared? That's the kicker. You can never, ever, ever, let me repeat this, you can never, ever, ever leave an I with an exponent on it. The only exponent I can have is to the first power. Why? Because every other squared or to the third or to the fourth, you can simplify down. For example, I is just I, right? What is I squared? Well, I squared, so I'll put that as I squared is -1. So what is I to the third? Well, isn't I to the third the same thing as I squared times I? So wouldn't I to the third really be -1i? I to the fourth. What is I to the fourth? Well, isn't I to the fourth really the same thing as I squared times I squared? So -1 times -1, so it's 1. And then guess what? This pattern will continue. So it really goes I, -1, -I, 1, and then it just keeps repeating. So I to the fifth, if I wanted to say what is I to the fifth, well, it's just going to be I, isn't it? Because I to the fifth, I could rewrite this out. I could rewrite it out as I squared times I squared times I. Well, I squared is -1, I squared is -1, I is just I times I is 1, I. So it's just I. And then I to the sixth, I guarantee you, will be the next term. It will be -1, and it just keeps repeating. So I should be able to ask you what I to the 98th is, and you should be able to tell me what the answer is. And it has to be one of these. It has to be either I, -1, -I, or 1. It has to be one of those four. So anytime you have I to any power, it has to be one of these four. It can't be anything else because they all simplify down. So now, go back to this question. I squared is -1. So now I have -3 times -1, which is 3. So now I have 8 plus 3, which is 11. 6i plus -4i, that's 2i. That is my solution here. That is what that multiplies down to. I love imaginary numbers. They are so cool. You just have to realize what they're doing. Now, I will tell you, let me see if I can erase this page here. Again, let's talk this through. We have the pattern we had was I. Then we had -1. Then we had -I. Then we had 1, right? So this is a pattern. And this was I to the first, I to the second, I to the third, I to the fourth. And then if I asked you what I to the fifth was, well, it starts all over. It's going to be I, right? And then I to the sixth is going to be -1. So how can we tell just by using a pattern? Like if I said I to the sixth, what we do is we take the remainder if we divide by 4. So 6 divided by 4, 4 goes in there one time, but what's the remainder? It's 2. So anything that has a remainder of 1, anything that has a remainder of 2, anything that has a remainder of 3, anything that has a remainder of 4. Okay, so let's see if this works. I to the 6th, remainder 2. Well, we said I to the 6th was negative 1. Negative 1. So 1, 2, 3, 4. So if I said, what is I to the 57th? I would just take 57, divide by 4. So 4 goes in there 1 time, so it goes in there 4 times, so that's 16. But the remainder is 1. So I know I to the 57th is the same thing as I. Boom. They're exactly the same thing. So that is how you can use a pattern to come up with, because I'm going to ask you some of those questions today or on your assessment. So that's how you tell. All you have to do is divide by 4. What is the remainder? All right. Multiply the complex number. Oh, this one's really important because the i's are going to go away. If you multiply, these are called conjugates. 3 plus 2i, 3 minus 2i. Whenever you have the same thing inside, and it really makes sense when you think about, if you go back to, this is a difference of 2 squares, right? So if I factor it, it's x minus 3, x plus 3. Well, if we multiply this together, we get this, right? These are called conjugates. The middle term goes away. Well, look what happens here if I FOIL this out. I get 9 minus 6i plus 6i. There goes the imaginary numbers. And somebody's going to say, but you still have imaginary number in there because look what happens here. You end up with negative 4i squared. Those cross out. I end up with 9 minus 4i squared. Well, I squared is negative 1. Negative 4 times negative 1 is 4. 9 plus 4. This whole thing is 13. Anytime you multiply conjugates together, the imaginary number disappears and you just get a whole number. It's very, very important when we start dividing these types of problems. Okay, so keep that in mind. So if I have 3 plus 2i squared, well, remember, that squared doesn't just square these things. You have to multiply it out. You have 3 plus 2i times 3 plus 2i. So if I multiply that out, FOIL, that gives me 9 plus 6i plus 6i plus 4i squared. Okay, so 6i, so that's going to be 9 plus 12i plus, well, 4i squared is negative 4, isn't it? That's a negative 1. 4 times negative 1 is negative 4. So that becomes 5 plus 12i. Multiplying complex numbers, you just have to do just like you normally would multiply, but be very careful. Whenever you have an I squared, that is negative 1. All right, let's try a practice problem. Evaluate the expression 4 plus 7i. Okay, so I have 4 plus 7i times 7 minus 3i. Okay, so if I FOIL this out, that gives me 28 times negative, that gives me negative 12i. 7i times 7i, well, that's 49i. And 7i times negative 3i, that's negative 21, negative 21i squared. I squared is negative 1, so negative 21 times negative, that's positive 21. All right, so I have positive 21 here, positive 28 there, that's 49. So that goes away. And then negative 12 plus 49, oh, let's see here, I don't want to make a mistake on this, so that's 37i plus 37i. So 49 plus 37i, looks like letter A there. Okay, now we're going to talk about complex conjugates, but we already talked about them. If I had 2 plus 3i, a complex conjugate would be 2 minus 3i. And the reason? Because the i's, the imaginary numbers, are going to disappear. And that is going to help us immensely when we're talking about division problems. So keep that in mind when we talk about division problems, a complex conjugate. So basically what happens is that middle term is going to cross out. All right, so why do we do this? Well, if you're trying to simplify something like 2 plus 3i over 4 minus 2i, the rule is that if you have a problem, you cannot have an imaginary number in the denominator. Well, how do you get rid of the imaginary number in the denominator? Complex conjugate. So for example, this cannot be an answer because it has an imaginary number in the denominator. So what we're going to do is we're going to multiply top and bottom by the conjugate. So I'm going to multiply top and bottom by 4 plus 2i. So I'm going to take the original fraction. I'm going to multiply top and bottom by 4 plus 2i. Now the top is really nasty, but look what happens to the bottom. You get 16 minus 4i squared. That becomes 16 plus 4. That becomes 20. I no longer, and then the top simplifies down to 2 plus 6i. I no longer have a imaginary number in the denominator, and that is key. You can never have an imaginary number in your denominator. So that's it. We get rid of them. So here's an example from our assessment. I have 106, and it wants me to write it in the form a plus bi. So I've got 106 over 5 minus 9i. Well, I know I have to multiply top and bottom by 5 plus 9i. Okay, 5 plus 9i. All right, so multiplying the top, well, that's not too bad. I've got 106, 106 times 5, so that's going to be 530. So I've got 530 plus 106 times 9. That's, oops, 54, 954. I. And then on the bottom, okay, so I know that this is going to, the middle terms are going to cross out. So I'm going to end up with 25 minus 9i squared. 9i squared is negative 1, so that's going to be 9, or 25 plus 9. So that really gives me 34. All right, so now I'm going to rewrite this as 530 over 34 plus 954i over 34. I don't have my calculator. I do have a calculator out here. I do. Okay, so I'm gonna do this out. Okay, so I've got 530 divided by 34. I hope that's right. That doesn't seem right. Divided by 34. Let's take a look here. Nope. Let me see if I multiplied this wrong up here. 106 times 5. That's 530. Did I mess up down at the bottom? Oh, 9 times 9. Bummer. That should have been negative 81 I squared, which becomes positive 81. So this should be 25 plus 81. Sorry about that. Oh, thank goodness for my calculator. So that's 106. So the bottom should be 106. I apologize. So this is 106. 106. So 530 divided by 106. What is that? 5 plus 954i divided by 106. That's 9, isn't it? I believe. So 9i. So my answer should be 5 plus 9i. Oh yeah, got it. Excellent. Thank goodness for calculators. All right. Complex solutions of quadratic equations. Now, you can have, when you solve a quadratic, it could end up being an imaginary number. So we just solve like normal. We don't do anything different. Now, if you are given a radical, like for example, it says evaluate the expression, anytime you have a square root, you just rewrite it, and you have a negative inside, you just rewrite it without the negative and put an I in front. So the square root of 25 is 5, so this is 5i. Boom, done. Now, if you're trying to solve a quadratic, you could have a complex answer, and that's not a big deal. I would use a quadratic formula. A is equal to 3, B is equal to negative 2, C is equal to 5. Negative B, which would be 2 plus or minus the square root of B squared, well, that's 4, minus, is it 4 times 8 times C? So that's going to be 20, that's going to be 60. Oh, I'm going to have a negative inside, all over 2 times A, which is 6. 4 minus 60, that's 2 plus or minus the square root of negative 54 over 6. You can never leave a negative inside a radical. So I'm just going to rewrite it as 2 plus or minus I square root of 54. Now I could probably simplify it down, but I'm just going to leave it just like that. That is it. You can have an imaginary answers to a problem like this. All right. Whew. That is it for this.